going to talk about next time is actually converting from one basis to another. All right, and so that's an important thing, and it's important really to understand what a basis is, intuitively, so that you can understand what it means to convert from one basis to another. Right, so that's what we're moving towards. Right, so that leaves you pretty much off the hook in terms of problems to do. So what that means is that you should really take the time to go back and just study what we were talking about tonight and just understand the vocabulary. The vocabulary is so very important. Right? So that next class, when I start talking about this, you can have a pretty good idea what I'm talking about. All right. It's not terribly difficult in terms of the process by which you convert from one set of coordinates to another, but it can be a little mind-bending when you consider the visual representation. So that's kind of why I'm here. The theorem itself, I mean, it's very linear algebra-esque. Beta is a set of vectors in the vector space V. Then for each x in V, there exists a unique set of scalars, C, such that a linear combination is formed. All right, so cool. If B belongs, beta is, again, a set of vectors that is a basis for V and x is a V, then the coordinates of x relative to the basis beta, or the beta coordinates of x, are the weights, C, that form that linear combination. Right? So really what it's just saying is when you have that relationship, that linear combination, part of that is going to be the vectors that make up your basis, and part of that is going to be the transformed coordinates. All right, so you're going to have a coordinate that you start with, or a set of coordinates that you start with, and a set of coordinates that you end with, and you'll have a transformation matrix, which really just ends up being your new set of bases. All right. So all of the above boil down to the following rule: x is equal to beta times matrix x sub beta, where beta is the coordinate matrix and x sub beta is the coordinate vector. All right. So, okay, cool. We do have to consider what on earth any of that means, aside from the linear combination part of it, which by now should be kind of like an old hat. You're pretty comfortable with that. But looking at this relationship, we could actually solve for really any component. If I wanted to, I could solve this for x sub beta. And that would be the inverse of beta multiplied by x. I could also solve it for beta, poor quality beta. A little too ostentatious. So we'd be looking at the inverse of x sub beta multiplied by x. The problem with this one is it doesn't always hold, all right? Because it might not be invertible, because we're talking about a vector, so there's only certain circumstances in which a vector is invertible, right? So that is not going to be necessarily always true. So mathematically it seems to be true, but not necessarily I'll say helpful. All right, just because of the constraints related to matrix multiplication. All right, so you use a different approach. So anyway, the examples here, I talk about, and we'll work on the skill, and then we'll get into why this stuff works the way it does, or how it works anyway. Find the vector x determined by the given coordinate vector x sub beta and the given basis beta. All right, so it's just plugging and chugging away. If I have these two pieces of information, all I got to do is multiply them, and I'll have what I need. So x is going to be equal to the product of beta and x sub beta which is 32 negative 4, 1, multiplied by negative 2, 5, which really isn't that bad. So I'll just do it by hand because I think we actually have it figured out by hand before I'd even get my calculator, this information typed into the calculator. So we're looking at negative 6 plus negative 20, so negative 26, and then negative 4 plus 5, so that'll give me a 1. All right, so it's like, okay, so what is that? What does it mean? What does it represent? All right, so I'm gonna speak of it in everyday language, normal people speak, although it may not seem very normal after you see what I have to say. All right, so this matrix B is the new basis. All right, so the new, quote unquote, new basis. All right, ordinarily it would be 1001, right? So usually it's the ij because we're in 2 space here. All right, so I, which is 1, 0, became 3, 2. J, which was 0, 1, became negative 4, 1. All right, so this is my new basis. I have a new system that's based off of these 2 vectors as they're defining attributes, I guess. All right, now this one, oh, and this is where it gets a little weird. Call this beta world. All right, so beta world. So this is a coordinate or a vector, but the vector is related to a coordinate. So I'll say coordinate in beta world. All right, and this negative 26, 1 corresponds to the coordinate in the real world. Right, specifically R2. All right, so it really is the real world, real space. All right, so you have a system that is defined based off of, well, overusing a term here, based off the bases, 3, 2, negative 4, 1. And so a coordinate in that universe, in that world, would correspond, if we were to just plot this coordinate under their rules, it would correspond to our coordinate of negative 26, 1. All right, in the way that we're used to plotting points. All right, so sometimes you're given the point in the real world and you want to know what it would be like in beta world. And sometimes, just like this one, you're given it in beta world and you want to know what it would be like in the real world. All right, so that's what we're up against in the second case. What I'm going to do is write the relationship, which is x of beta, so the coordinate in beta world, would be based off of the product of the inverse of beta and x. All right, so it's still really the same structure, except now we're applying an inverse. All right, so all right, so we're just going to run this calculation, but this time, it is worth our time to put it in the calculator because we know how troublesome it could be to come up with an inverse. All right, so I'm going to pop this in there. I may have actually already popped it in. Let me see. No. Looks like I popped the next one in there. Well, and that looks good. And then 2, 3. And then we're just running the calculation. So matrix A as an inverse times matrix B. And you get negative 8.5. All right, so in the previous example, what we kind of gathered from the operation is that multiplying a beta vector by the basis for beta converted it from beta world to the real world. So it makes sense that if I want to do the opposite, if I want to go from beta world, I have the X. If I want to go to real world back to beta world, I would just do the exact same thing, but in reverse, right? So instead of multiplying, I would divide. The matrix method of division is multiplying by an inverse, right? So the exact opposite procedure, right? So this is what the coordinate would be in beta world, right? So we could play around with the graphs of these, and it's definitely worth a little bit of time to do that. So I'm just going to draw a quick sketch. Probably pretty poorly, but it'll be something. So again, beta world, real world. Ooh, little stray marks there. All right, so if I draw a sketch, plotting vector 2, 3 is going to be super easy, barely an inconvenience. I really love that channel. I have a line draw tool, I should use it. I have a line draw tool, I should use it correctly. And there it is. And not really. I don't know why I'm caring so much about the detail here. It's a freehand drawing for the most part. Anyway, all right, but anyway, that's 2, 3. All right, so specifically X. Now we have these basis vectors. -1, 1. I'm sorry, 1, -1, and 2, -1. So I'm gonna sketch those out too. There's no reason that should have happened. So here's one basis. And 2, -1. I really probably should have wrote that in another place. So let me put the 2 and the -1 here. And instead of actually labeling them with their numerical values, executive decision here, I'm just gonna call one of them B1 or lowercase b1, and the other one B2. All right, because the columns of the transformation matrix, because that's really what it is. I mean, when we were converting by by rotating coordinates and reflecting them, we were creating a matrix to multiply by a vector to transform it into another coordinate. But the reality is we were changing bases. And so what's actually happening, because it's kind of weird and cool at the same time, but what's happening is you're not really changing the vectors. You know, like when you multiply a vector by a matrix, you're actually not changing the vectors themselves. What you're doing is you're changing the scale around it. You know, you're changing, instead of going by I and J, you're going by B1 and B2. But it's kind of like the point is remaining fixed. It's just everything else is morphing into a different reality, right? So, I mean, you kind of see visual examples of that in movies and TV all the time, where the person, you know, like Star Trek was really, really big on this, but I'm sure there's other shows, like if something happened in the past, you know, like there's time travel involved, something happened in the past, they change the past, and then the person in the future change, you know, they're still in the position, but then you can kind of change you can see their reality changing around them. You know, that's really what's happening here, except not as interesting, I guess, because it's just multiplying matrices. But, you know, like that's the theoretical component of it, right? So what we're going to do here is think in terms of B1 and B2 as opposed to I and J. So instead of saying I have a coordinate 2, 3, that's 2 over 3 up, I now have a coordinate negative 8, 5. All right? Now that negative 8, 5, it is negative 8, 5. That negative 8, 5, I'll just kind of jot it off on the side here, or maybe below it. Yeah, below it. Is negative 8 B1 plus 5 B2. That's that linear combination we were talking about before, all right? Now, if your bases are 1, 0, 0, 1, then that's negative 8i plus 5j, but they're not. Our bases are whatever they were that plotted 1, negative 1, and 2, negative 1, or whatever it was, right? So what this is telling me is that I have to take negative 8 steps along B1 and then 5 steps along B2. And it's at this moment that I realized that maybe I didn't give myself enough room to do this, but I'm going to make it work. So 8 of these. So 1, we'll plot a point. 2, in the negative direction, so opposite of the positive direction. 3, 4. I'm going to end up overwriting stuff, but that's all right. 5, 6, 7, 8. All right. Now, I'm also going to move 5 steps in the direction of B2. All right. So I just have to ballpark what B2 looks like. All right. So I'm just going to take that. It's vector sums. So it's going right back to the beginning of the course. That's what B2 looks like roughly. I need 5 of those. 2, 3, 4, 5. Like I said, poor quality diagram. All right, but this would be my endpoint. All right, and that would correspond with a vector. All right, and so this would be, in theory, this should be 2, 3. All right, now if I put even a teensy tiny little bit of effort into creating a decent looking graph, you would see that. The best way to do it would be to do it on the same set of axes. All right, so you plot your 2, 3 with graph paper. because it actually, this is like the one situation where graph paper would be very helpful. And it's just, I haven't quite figured that out here. I know I can make the background into graph paper, but it'll make it for the entire notebook. And then when I try to take it back, it'll remove it for the entire notebook. So it's not quite there yet. But if you do it on graph paper, plot 2, 3, plot your B1, B2, and then count in terms of B1s and B2s. When you have your linear combination, these movements should map directly to the point 2, 3. All right. And so what ends up happening is, what people will do is actually redefine their x-axis to be one of the given vectors, the new bases. Right? So what you could actually do is make this a horizontal. Like if you really wanted to think in terms of B1 and B2 here, you wouldn't necessarily want to look at it this way, because your reality is in terms of verticals and horizontals. So just this is the truly mind-bending part. In another universe where this is the reality of it, right? B1 and B2 are your I and J. B1 looks just like I to them. B2 looks just like J to them. All right, their B1 is 1 unit movement along the horizontal axis. Their horizontal axis, B2, is 1 unit of movement along their vertical axis. Right? So when they actually plot points, their graphs would look like this. But to us, it looks like this. All right? So it is really just a matter of perspective, but it's a pretty intense way of looking at things. All right? So, and interesting. Hopefully. So I'll put stars on B and C. You don't have to create graphs for them, but I would encourage you to do it at least for one of them. Just to feel this out on your own. Look at this. Another way of saying x of beta would be the coordinate value of x relative to beta, right? But I look at that as a coordinate in beta world, all right? So I over. All right, so now they're defining set beta as this, really it's a vector value situation here, but this is forming the base of polynomial space too. All right, so it's a little different now. But what we want to do is find the coordinate vector of P of t relative to beta, right? So when we go back and we simplify the concept, maybe a little too much, but I do it for a purpose because I think it's kind of easier to keep track of it that way. All right, but polynomial space 2 is talking about a real space defined only in terms of polynomials with the highest power equal to 2. So highest power equal to 2. All right. So the way that would look in general terms you'd have, I mean, you could use any notation you want. I'll use typical polynomial or quadratic notation. So I'll say C BT AT squared. All right. So like AX squared plus BX plus C, just with T's instead. All right. That's the model for polynomial space 2. All right. So that works, because then what that'll do is it'll define beta as 1, 0, -1, because I only really care about the coefficient. You know what? I'll actually write the variables in, and then we'll drop the variables. But for now, I'll just write them this way. So 0 t -t. I'll write -1 t squared. 1 and then -1 t squared. and then 2, negative 1t, and then 1t squared. All right, so that forms my basis, but we're gonna drop the variables because all we need is the coefficients. Because as long as you know that the first entry, once you have the model that's telling us that the first entry is going to represent the constant term, the second entry is going to represent the power of 1 term, and the third entry is going to represent the power of 2 term, then you have everything you need. So this corresponds to a transformation matrix, or the basis matrix: 1, 0, negative 1, 0, 1, negative 1, 2, negative 1, positive 1. All right, find the coordinate of vector p of t relative to b. All right, so they're telling us that x is equal to, and again, I'll write it with the variables: 1, 3t, negative 6t squared, which corresponds to just the vector 1, 3, negative 6. And we're looking for x sub beta. We're looking for the 1 in beta world. All right, and so based on what we covered on the previous page, it's not going to be difficult because we already did all the hard work. So, you know, and that was the setup. So x sub beta is going to be the inverse of 1, 0, negative 1, 0, 1, negative 1, 2, negative 1, 1, multiplied by 1, 3, negative 6. Okay, so that's calculator work. One, 0, 2, 0, negative uno. Nope, 0, 1, negative uno. Negative 1, negative 1, positive 1. Double check. Looking good. 1 by 3 is what I want. Nope, 3 by 1. I don't know why I said 1 by 3. 1, 3, negative 6. That looks good. All right, so, oh, well, I could just repeat that calculation. So 3, 2, negative 1. All right, so these are the weights on my basis corresponding with the real point. All right, so the coordinate vector relative to beta. All right, so we'd be saying that this is the same. This leads us to 3 times beta 1, B1, sorry, plus 2 times B2, plus negative 1, so minus B3. All right, so again, this is my B1, B2, B3. Right, and it's something that you could verify. Put your weights in, simplify, and you'll see that it does play out. So, you know, there's something to that. All right, but it's just a different application of the concept. All right, but and actually, I might as well just go through the little checkarooski here. So if I multiply by its corresponding weight, what I would do again, because these vectors strip down to their coefficients, they're wonderful, but I eventually want to have it back in polynomial form. So this would be 3 times 1, 0, negative t squared plus 2 times 0t negative t squared and then minus 2 negative t squared. Yeah. All right, so if I run through the calculations here, 3 times 1 is 3. Well, the next part I could just kind of talk through. I don't think I need to write it all out. But 3 times 1 is 3. This is irrelevant. Minus 2 gives me the 1. 3 times 0, irrelevant. 2t plus t, 3t. Negative 3t squared minus 2t squared, so negative 5t squared minus another t squared gives me negative 6t squared. All right, so basically what we did was we came up with just now an effective way of representing a polynomial function in matrix vector form. So this is the same as saying P of t. All right, so that's a nice application of the concepts of change of basis, because really all we're doing is identifying what the appropriate bases would be and then going from there, right? So if I wanted to, I could even define it in terms of standard bases, right? But that could be a little iffy, because that would assume that a lot of things would be zeroing out, and also to assume that your coefficients are equal to all equal to 1. So if you did, what I'm getting at is if you did 1, 0, 0, 0, 0, 1, I'm sorry, 0, 1, 0, and then 0, 0, 1, you could define your vector, I'm sorry, your polynomial in terms of the standard unit vectors. But this does the job too, so you can go either way with it. Right. The benefit of doing something like this, even stripping it down so that the variables aren't there, is that now I can do calculus to it. All right, so I can apply derivative and antiderivative techniques, because now I have a method by which I could represent a continuous function in vector matrix form. All right, so when we start talking about Jacobian determinants and things like that, we're going to start to see how we can apply the concept of a partial derivative to a vector matrix form of a polynomial function. All right, so number 2, I'll just put a star on, because it's the same idea, except you're already given the polynomial vectors, and you're just looking for linear dependence versus independence. So that's not really anything new. The new concept here is being able to write your vectors appropriately. You're always going with the highest power. So in this case, the highest power is 3. So the little tip, well, it's not really a tip because it's flat out said or stated, but that defines what polynomial space you're working in, polynomial degree 3. All right, so even if that wasn't given there, you would still make that determination, right? Because there's nothing beyond the power of 3, but you couldn't stop at power of 2, because then you wouldn't have a way of representing the third power. All right, so our change of basis, just generalized, There's notation associated with it, but this is not really anything new. Like we just did this. It's just the idea that we're converting from one basis to another. I'm not overly in love with these formulas just because, I mean, just look at them. I feel like on the previous page, we kind of developed a reasonable way of conceptualizing this. And I feel like this goes kind of counter to that. It's basically saying, all right, all that stuff that you understood, I'm going to purposely try to make you not understand it anymore. Right? So feel free to not use these formulas, because really the idea is that we're using a basis vector, or a basis related to a vector, and we're converting from one form to another, right? So, yeah, it's really nothing more than that, all right? So, yeah. So, general procedure for converting from one form to another. You know, it still relies on a notation, but the idea is that you're converting from one basis to another. What we do is we're actually just really applying the same idea that we did when we were finding inverses, right? So we're looking to get the identity matrix, form the n by 2n augmented matrix, and then transform this augmented matrix into reduced row echelon matrix. All right, so it'll look like this. The matrix to the right side of the reduced row echelon form is the transformation matrix, getting you from one basis to another. All right, so that's how you convert from one, well, at least that's how you come up with the multiplier that allows you to go from one basis to another. Because the one challenge that we had was we were working with the standard unit vectors and going back and forth from that to our transformed, our beta world, right? But what if we're dealing with two worlds that are not the real world, right? So if we have beta world and delta world, for example, how do we convert back and forth between those two? Well, the two possibilities: one, use the real world as a way station. Convert, if I'm going from B to C, beta world to, say, gamma world. Beta world to gamma world, I can go from beta world to real world, and then real world to gamma world. This technique kind of streamlines the process and allows you to come up with one matrix that'll get you from those two realities directly. All right, so I'll just take you through an example for that so you can see what the hell I'm talking about. But this right here, what we're trying to transform into is the I anyway, that's the real world. That's our standard unit vectors, right? This is the combined matrix that has the attributes of both B and C, right? So what we're just trying to do is take those two independent matrices and pare them down so that they're basically put into one matrix, all right? So that's a poor quality color. So this is B to C. Use colon. All right, so this is what we'll just put it in our calculators. Because like I said a few minutes ago, this is the same as saying, you know, like I want to find the inverse of a function, inverse of a matrix I would be using the same skills essentially here. So I don't feel the need to assess you on that a second time.
Question.
Yeah.
Isn't it P from C to B?
Oh, Christ. Thank you. Let's move this over. Here, 2 and a 1. Okay. So then I just want to do a quick RF. On A. And we get zapped. Yeah, so that makes this a typo. That should be C to B. All right, so what this will give us is a matrix that we could use to transform any coordinate that's given in C world into a coordinate that's in B world, all right, or beta world if you want. All right, and so the other way around is just a matter of swapping columns. All right, so the first two columns get swapped with the last two columns. All right, so that part's not too bad. Yeah, I think the hardest part about that is actually just physically writing it. Yeah, I'm pretty sure. Yeah, they have row swaps, but I don't think they have column swaps. That would have been nice, but alas. I mean, in the end, it's only a 2x4, so you just retype. Okay, I think I got that. And so we end up with that matrix. And again, that's the matrix that will allow you to convert a B coordinate into a C coordinate. All right, so that's really all there is to it because it's very procedural. It's also worth the time to actually perform some transformations and just kind of get a feel for it. But obviously you don't want to do that for every problem because that one graph I created, what was it, 2 pages ago, 1 page ago, it took long enough that if you had to do it for every single question, it would be kind of nightmarish. But what you can do is even take one of your basis values and convert that over and see what that gives you. Take an arbitrary coordinate, convert that over, see what it gives you. But ultimately, procedurally, there's really not much of a way you could screw this up, right? So as long as you know that you're taking the two matrices and putting them together and then running an RF on it, the only way that you can mess this up would be to zig when you're supposed to zag. Like you just did it backwards. And even that on a test, like -1 point. You know, so like I said, there's really no way to screw it up. And you could even see, I screwed it up. And the worst part is, it was right there. Like, I would imagine that at some point I was copying and pasting. I just copied and pasted the wrong thing. I don't know. I can't get out of my own way sometimes. Sometimes I don't even want to. All right, so put a star on the next one. And then we move to a concept called the Markov Chain. Okay, so Markov chains, how to do it, what for, all that stuff. A vector with non-negative entries that add to one is known as a probability vector. A stochastic matrix is a square matrix whose columns are probability vectors. Right, but the term stochastic, just because people who write stuff for a living tend to write this stuff a little bit better than I do. So I just did a quick Google search on stochastic models, and really it's just, very simply put, a stochastic model represents a situation where uncertainty is present. In other words, it's a model for a process that has some kind of randomness, right? So basically, I've always known of stochastic models as probability models, right? They involve probability in some capacity, right? That's the randomness component. And so it would make sense that the columns, if we're going, you know, in this course we're talking about the columns of a matrix representing vectors, and if a stochastic model is talking about probability, and the columns for us typically have represented vectors, then it would make sense that we'd be looking at probability vectors, right? A sequence of probability vectors together with a stochastic model P such that x of 1 is equal to P x of O, x of 2 is equal to P x of 1, and so on. You're calling upon prior information, so what we're looking at is a recursive model, right? So it's just calling on a previous calculation to get you a new calculation, all right? Also known as an iterative process, but you can probably see why I don't like saying that one too much, all right? So recursive is, you know, probably a little bit better. Although iterative tells you a little bit more about what it is, because iterate or reiterate, you kind of know what you're talking about there, because that's a word that you use in everyday language. Maybe not iterate, but definitely reiterate. You know, so, you know, just carrying out a process over and over and over again. But the concept of an iteration is that you're taking a previous calculation and using it in the same model to generate a new result, right? And you do that over and over again until you settle in on what the true outcome is, all right? So it's pretty weird, but also pretty interesting, all right? Markov chain is described by the first order difference equation, all right? So x sub k plus 1 is equal to p times x of k. Right, for k is equal to 1, 0, 1, 2, and so on. Right, so that's really just the same thing, except we've generalized it. We're saying that we're getting a result that is one further calculation down the line than what we started with. All right, just be careful. First order blank equation, it's kind of hard not in your mind to fill that blank with differential equation. They're not the same thing. All right, difference equation. We'll talk about differential equations before this is all over, but oh, looks like I updated the word problem. Look at that. I just switched back to FiOS again this past weekend. I think I'm gonna probably switch back again, because It's just aggravating. Like the remote works a lot better for FiOS, but the price difference, I don't know. It's like when they came to the door, they gave me a quote of $137 a month. And then I got the notice that says the bill is going to be $157 a month. And they wrote down, like they itemized it. So that 137 included taxes and all the government fees and stuff like that. So I think somewhere along the line something got screwed up. But the reason that's a problem is because my Altus One, the optimum bill is like 161 per month. So 157 versus 161, that's not a significant difference. Except we have HBO with Altus and we don't have HBO with FiOS. Right? So there's a lot of things going on. And actually a lot more channels with Altus.
If you call Verizon, they'll bring their price down to at least 135.
Yeah, and I'm still within the 30-day grace period. So if I threaten to cancel, then yeah, they're gonna roll over. They're gonna roll over like a sick puppy.
They might even bring it down to 125.
They'll bring it down to free. That's what I want. Yeah, so we'll see. But I'm a procrastinator when it comes to that. I'd be like, yeah, I'll do it, and then I won't. So I don't know. All right, anyway, we got two competing companies, A and B, for example, Altus One and Verizon. After 1 year, some customers will keep using the same product, but some will switch to using the other product. The proportion of customers who keep using the same product or switch to use the other product after 1 year is summarized in the following table. Right? Suppose 3/5 of the customers use product A and the other 2/5 of customers use product B in the beginning. Then we want to know what is the distribution of customers who kept and switched their services after 1 year. All right? So it's very simple because we have a matrix that's given to us and it's a probability matrix. The columns have to add to 1. Check. All right, so if I just add up my first column, 1/4 plus 3/4 gives me 1, same deal with the second column. So P, my probability matrix is going to be 1/4 and 3/4. For the first column, anyway. Second column, 1/3, 2/3. All right. Now what we have here for that 3/5 and 2/5, we have a vector that's known as the initial vector. All right. So my initial vector XO. I mean, reality is it's just a vector. The fact, initial or otherwise, is determined based off of the subscript. If the subscript is 0, then it's initial. Right? So you can call it an initial vector or you just call it a vector. It doesn't make a difference. But what we're after is known as a steady state vector. All right? That's the vector that would exist if you were to continue the iterative process in perpetuity. Right? So you were to go on forever and ever again, multiplying, taking the result and continuously multiplying it. What vector would you eventually settle in on? Right? That's what's known as a steady state vector. Right? And the Markov chain process gets us to that. Right? So what we'll figure out is based off of these characteristics, what the long-term proportions are going to be. In the long run, what percent of the population is going to end up with FiOS and what percent of the population will end up with Altus. All right. So I want to find X sub 1. Or at least part A is only asking me for that. All right. So X sub 1 would be equal to P times X sub O. All right, so then what I have to do is carry out this multiplication, which seems fun. put it in the calculator. It's not too bad. So I'll do a 2 by 2. I'll put them in as, well, I'll put them as fractions. 1/4, 1/3, automatically puts it in decimal. 3/4, 2/3, then matrix B, 2 by 1, 3/5, 2/5. All right, so all I'm doing is A times B. Ah, I hit the wrong thing. All right, and so we have a transformation matrix and we have a vector. Right, this is the basis, and so that's the whole thing. We're really still applying the concept of change of basis, right? Or at least coordinate systems. It's contextual, so it doesn't feel like we are. But instead of having 1, 0, 0, 1, our new reality is in probability world, where the basis of vector 1 is 1/4, 3/4 rather than 1, 0. Right, so it's the same but different. All right, so we carry out that multiplication and we get this result. All right, but the issue is I now have to, so I can write that down. I'll just put an approximation, but I now have to use that number again for the second part. So 0.283 repeated and 0.716 also repeated. All right. So the way the vectors are set up, it's keep then switch. All right. So what happened is, and again, keep and switch. It's relative to where you started. All right. So we have an increase in folks that are keeping their service, and we have a decrease in those that are switching. All right. At least after 1 year. So what I would do at this point, in order to find the distribution that kept and switched after 2 years, same calculation, roughly, but this time it's x of 2 is equal to p times x of 1. So I still have my probability matrix, 1/4, 3/4, 1/3, 2/3, but this time it's, instead of being multiplied by 3/5, 2/5, it's going to be multiplied by 0.283 and 0.716.
Keep and switch or keep or switch?
Keep, switch. First entry is keep, second entry is switch. Oh, and I think I said it increased and decreased. It decreased and increased. So the percent that are keeping their service has gone down, and the percent that is switching their service has gone up, because the initial vector was 60%, 40%. Now, after 1 year, based off of the probability matrix, we're looking at roughly 30% and 70%. Right? So it's a drastic shift in the opposite direction. Right? I said that backwards a few minutes ago. All right. So anyway, I have to multiply this matrix by this vector. Right? I don't want to have to type that in to matrix B. So what I'll do is I'll store it in as matrix B. So store, call up matrix B and hit enter. So now anytime I use matrix B, it's this matrix. All right, matrix A is my probability matrix. Matrix B is this new matrix. This new vector. So now when I carry out the multiplication, A times B, well, I don't really have to do anything new. All right, just by storing it, I'm able to let the calculator do the heavy lifting. All right, so we're looking at about 0.3 097.6903. So yeah, that's after 2 years. Now for C, it appears C is missing a question mark. What is the distribution if the market is said to be stable? The distribution of the market would be constant forever, right? So what that's telling us is to find what's known as a steady state vector, right? So we carry out this operation repeatedly. Eventually it's going to settle onto a distribution, right? These numbers are fluctuating, but eventually they'll stop fluctuating. They'll settle onto a particular value, and once they do, that'll be your steady state vector. All right, so for C, we're going to find the steady state vector. All right, so what that means is store this value, or this array of values, into matrix B. And actually, I mean, now you could just do a little recall, second enter, do that. Recall, oh, get out of here. Recall, multiply. And you can see there isn't much difference between these two values, but there is a difference, so we do it again. So store, multiply, and we keep going until there's no change. All right, so there's slight change, and we're pretty confident that we know what the steady state vector is going to be. It looks like it's going to be about 0.3 and 0.7, but about really isn't good enough. I want to know what it's going to be exactly. So I do it again. Even less change, but I want no change. All right, very, very close. Yeah. One more time. One more time. Oh, so close. One more time. One more time. So close, it's probably, as you said, one more time. And there it is. All right, so no change in my vectors. So this is my steady state vector. This is what we could expect our long-term vector to be. All right, so in the long run, we could expect roughly.
Oh, it's such a pretty fraction.
Oh, it is? Should have investigated that. Let me do that now. Some math. Oh, jeez. I don't need to do a screenshot on this. I just write that.
And the original fractions were not as pretty, but they were round.
Right.
They got
All right, so 4/13 of the population, which amounts to about 31%, is going to keep their service. About 70% or 9/13 of the population is going to change their service. All right. So, yeah, you kind of look at it in the context of the real world and say, wait a minute, what happened here? Because in the first year, or after the first year, sorry, we had 60% of the people keeping their service and 40% of the people changing their service. And then it turns out that over the long haul, it's gonna be a complete role reversal where most people are switching their service and a smaller minority of people are keeping their service. then you think about the reality of the situation. You know, like FiOS has 2-year contracts, right? Altus doesn't, but maybe there's a promotional period between the first and second year that expires. You know, maybe you had, I mean, I definitely had free HBO, Showtime, a couple of things for the first year, and then it went away. So at that point, you start thinking, okay, maybe I'll switch, right? But odds are, you know, you get 1 year in, you're not looking to switch because you're still getting all the incentives for having already switched to that program, right? So, you know, like the physical, or not physical, but the realistic contextual aspects of this could explain why there's such a change from the 60% to the roughly 30%, right? But mathematically, this is the process. Now you might say, well, that's a hell of a process because, you know, like how many iterations did it take to get there? Like, holy moly, look at this. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Honestly, I don't even know if I'm counting it right because no, one of them is storing. So I'll cut this in half, but I'll get a reasonable estimate. 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So we're talking about like 10 iterations, really, because part of that process is me just storing the value. All right, so it took really 10 years to see what the stabilized market would look like. All right. What if it was 100 years? What if it was? What if it was anything more than 10? I mean, that's really what it comes down to. So it's like there's got to be a better way to do this. Well, I'll find out in a second if I've already done this. In your calculators, just hit program. Do you have one that says Markov? Damn it. All right, well, it must have been the other class I did it for. So, yeah, because usually in the beginning of the course, I dumped the necessary programs in. But what I did was I wrote a program for the Markov chains that will do these calculations for you. It's just you have to, I mean, you obviously have to type in your initial vector and your probability matrix, but then it's programmed to do the iterations for you. So you just hit enter, 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 as opposed to store, recalculate, enter, store, recalculate, enter, and so on. So what I'll do is while you're taking the quiz, I'll dump those programs on your calculators so that we can use time effectively, I guess. All right.